All right, we're going to talk about Honey Badger Byzantine General's problem. And we've talked a little bit about some of the other solutions to the Byzantine General's data distribution problem and some of the alternatives like Google's F1 database. It's interesting because the original solution in the Bitcoin paper uses proof of work to solve this. And there are some problems with proof of work, not the least of which is that it is work, and consequently, as you do lots and lots of work, you burn up lots and lots of electricity and make lots and lots of pollution. And it also has cost associated with it. A second generation solution to this is something like a proof of stake, which Ethereum is actively pursuing. IOHK has their Cardano system that has a mathematically proven workable solution to proof of stake that is very, very strong. So those are the second generation. There are some third generations, like Ripple, that has a solution to this that is a data distribution that is much closer to what you see in this Byzantine honey badger problem. But it is not exactly this, but it is a consensus algorithm that does not require either proof of stake or proof of work. And there are certainly just out-and-out proof of authority systems where we just accept that there is a central authority that does the signing, and those also exist. EOS, which I'm not very fond of but is out there, uses a proof of authority system, and setting up an EOS node costs around $5 million. So there are very few people that set them up, and they are making a good deal of money, and there is some wonderful performance benefits. My problems with EOS is that their smart contracts are not sandboxed, and they're written in C++, which means sooner or later there's going to be a giant crunch sound when somebody figures out how to break through the security and do a buffer overrun and spend somebody else's money on that system. That's my forecast. It hasn't happened yet, but C++ just isn't a very secure and sandboxed environment for building this kind of software. That concerns me. So my concern is a technical concern, not EOS's algorithm. Their proof of stake makes perfectly good sense for this kind of an environment. Or not proof of stake, but proof of authority. And there are entire systems that are based on proof of authority. IBM's Hyperledger is purely a proof of authority type system. And it is open source these days. You can even, if you're willing to spend the big bucks, run it on Microsoft Azure, which I find interesting. It is an extremely hard system to set up to run on your own. And consequently, they have some business moat around their process of setting it up and running it for people. But it is the most hodgepodge collection of randomly put together things and duct tape and glue that you have ever seen in your life, so I have some problems with it from a technical perspective there. It is difficult to use not because the technologies are difficult, but because they plunked a whole bunch of different things together and just kind of stitched them together. There was no overriding design. It was just like, oh, we need a database, therefore, and it has to have these criteria. So we're going to grab this open source database and stick it in over here. And we need this component, we'll stick it in over there. And this component, we'll stick it in over there. There was no good leading way of designing it. And consequently, it has 7 or 8 disparate technologies that make it very difficult to use. Now, out of all of those proof of work, proof of stake, proof of authority systems, all of them are trying to get to consensus. And the consensus is really that at a certain point in time, all of the nodes will agree that the data is one form or another. Not that it's perfectly right, but they all agree that this is the piece of data that we are going to use going forward. And they all agree at the same time. And they can't cheat by looking at the data early and deciding which one they're going to pick. So those are the real criteria that set up the consensus. And proof of work does this by doing a bunch of work that is complex, and the first person that finds an answer distributes that answer, and everybody else can quickly verify the answer, And at that point, they say this is the answer. Proof of stake skips the work and says, by golly, if we catch you cheating, we will punish you by taking away your stake. Proof of authority doesn't have a stake or a work. It says, by golly, we're going to pick people out based on their reputation, and we will allow them to participate, and we will be the deciding authority because we are the authority on who else can participate. So it's proof of success by favoritism. Certainly, governments, that's the way they work. They do not look fondly on you printing out your own $100 bills because they say, we are the authority of the United States government, and if you print your own, by golly, we're going to come after you and punish you. And that's a proof of authority system. So these systems are not necessarily new, but the purpose is to get to this state of consensus. And the other system for getting to consensus, and this is a new one, is this distributed threshold ECDSA signature system. And let me give you the high-level overview of how it works. There are a number of them out there being worked on, and there are many pieces. The first thing you have to think about is how multi-signature works. And if I have, let's go down all the way down here and look at this little matrix with n equations in n unknowns. Now, if I had more than n equations, provided that they were consistent, okay, I could have, say, 2n equations in n unknowns and still solve this system of equations. In fact, as long as I decide that I have some number of equations that's larger than what I need, it's still solvable. So from a threshold perspective, if my threshold is just enough equations to solve to get the system of equations to work out, I can have as many additional equations as I want. Most threshold systems, they do this by saying, if I have 3 that I need and I do 5 equations, so if 5 divided by 2 is 2 plus 1 gives me 3 unknowns, then I have to have at least this half plus 1 to succeed. And that half plus 1 could be any set of 3 of those equations. It doesn't have to be a particular set. Now, anyone that has one of those equations can't solve it. In fact, if you have 2 of the equations, you can't solve it. You have to have at least 3. So if each one of these equations is being handled by one node in our set of nodes, that node alone cannot cheat because it can't solve the set of equations. In fact, for this set of equations to be solvable, we have to get half plus 1 of the nodes to come up with a solution to their piece. And at the moment when half plus 1 have a solution, then we can distribute that solution and we can say, by golly, that solution is now available and all of you can suddenly solve the set of equations. Now, if I have 5 machines running and 1 dies, but 3 of them succeed, and I get 3 equations, I can solve my set of equations. And at the moment when I solve my set of equations, the 4 machines that survived can all know what the result is. Now, I may not have a good set of machines afterwards because 1 died in the middle, but at least up to that point, I get a solution. So there's also redundancy built into this. Now, if I have 5 machines running and I need 3 to solve my set of equations, and a 6th machine shows up and says, oh, I'd like to participate too, it could start off where it is and try to solve this, but it's late to the game, or it could wait until the next round and participate. So we can add machines after the end of a round is usually how that happens, but as long as we have at least that 1/2 plus 1 to do the solution, we're there. Now, there's been some research at Carnegie Mellon that has mathematically shown that in any set of nodes, if you were to pick randomly 9 of those nodes to do this, okay, that set of 9 would provide the same security as any larger set of nodes, provided that you randomly pick. So if I take 19 nodes, randomly chosen, so that half of 19 plus 1 is my 9, and I set that as my threshold, I could have 1,000 nodes, pick 19 randomly, and make that into a group that does my computation. And instead of having 1,000 computers do the work, I can just have those 19 race to find the 9 that are going to give me the solution that will solve this set of equations. So we can reduce the number that we can do, but also if we can randomly pick out of our 1,000 nodes now, we can randomly pick and have a whole bunch of shards running, all at the same time, doing subsets. Basically, you look at 1,000 divided by roughly 20, and you say, boy, that is a lot of them that can be running on different problems all at once. Now, the original blockchain is a singly linked list, but there's nothing stopping you from building this as a directed acyclic graph instead. And IOHK has done a bunch of research showing that this actually works with directed acyclic graphs. So the research is out there to say, by golly, if I use this system and I solve this equation, I can pick any set of 20 or 19 or 20 or something like that, and I can get the same level of security as the entire system running all at once. So that is how that works. Now, the system of equations happens to be a multi-signature, and that's an important detail to know, is what we're actually using for our equations is a digital signature algorithm. And there is this detail about random numbers. Let's talk a little bit about the random numbers before we actually get into this. Now, we know that we're going to have this choice, and at every round in our processing, we want to pick out a set of computers. Now, usually what we want to do is we want to pick disjoint subsets, and we need them to be random. We need them to be really random so that nobody can cheat. Now, at the end of a digital signature, you end up with, yes, this public key. And the public key is an elliptic curve. Let's say you're doing 256-bit. It's a 256-bit number that is a signature. But there's nothing stopping you from, at the end of one of these things, saying that that signature, which is a 256-bit number, is actually a random number. And if we start looking at the signatures as random numbers instead of just it's a signature, then this signature becomes our way to have a random number. Now, in a threshold system, if that signature at the end is generated by a subset of the computers, say 19, and those 19 computers at every round, their goal in life is to generate a new random signature, then we now have a distributed random number generator. And a company called Thesis went to the effort of showing, with basically proving, that this system of random number generation produces actual random numbers. These are not pseudo-random numbers, because if each computer out there is generating their part of this signature independently, then the random number that you get at the end is an actual random number. Now, there are other systems out there that generate real random numbers, and they are in use all over. And one web company uses lava lamps. Lava lamps? Did I say that right? Lava lamps, yeah. The things that you heat up at the bottom and they produce the bubble, and the bubble goes up through and it's got a color. And they have walls of lava lamps with cameras. And the camera takes a digital picture while the lava lamp is going. The digital image is then hashed, and that produces a random number. And they use this for their elliptic curve public key encryption as an input. And we've done some mathematical work some physicists have to show that that random number from the lava lamps is actually a real random number. Okay, it is at the quantum level, unique, and generated in a quantum fashion. So there are other systems that generate real and true random values. This is not like a pseudo-random number that is generated by some computation inside the computer that is basically deterministic. Those are real. And this is another system that can actually be run on not a computer, but a network of computers. And above a certain number of computers, which turns out to be around, for reasons that we don't understand, 9, you can actually get real random numbers out of this. Probably the reason is because this is also, since it would be a distributed network, it's also picking up on network distribution random behavior. And we know from some studies done at AT&T Bell Labs that a electrical network has real random behavior, as in the fluctuations of the voltage above and below 110 volts. That fluctuation rate in the distributed network of power is a real random number. We know from some other work done at Stanford that packet timing across the internet is a real random number. So if we have a bunch of computers and they're all competing to pick the set of equations that's going to solve this, and they are distributed, then they are subject to this other stuff that's going on that is real random, and consequently their behavior and their results is going to come out to be a real random value. So this threshold encryption system, okay, can produce both the random numbers to pick the subsets, and it can also be used as a multi-signature to pick signatures over time, and these signatures can be used for things. What kind of things can you use signatures for? For instance, you can use it for doing actual encryption to protect data, so that you can have private data on public networks that is protected by this kind of a system. And the kind of data that you would probably want to do is something like, well, store your Bitcoin wallet, so that there is no node in the network that can get access to it, but with a proper set of signatures that is a multi-sig, it can be used. So this is the kind of stuff that people are actually wanting to use this for, and that's why the multi-signature and this stuff, you gotta kind of have the background in that. Now, you go, okay, so these different systems are going to be doing this computation, and each one can see into the computation. And isn't that going to leak data? Let's go back to